Look up at the night sky. It's a breathtaking canvas. We see stars, planets, and distant galaxies. But is there an end to what we can see? Yes, there is. This boundary is known as the cosmological horizon. It's not a solid wall out there in space. Think of it more like the horizon you see on Earth. As you move, the horizon moves with you. This cosmic horizon defines the limit of our observable universe. It tells us how far we can peer into the depths of space and time, given the current age of the universe and the speed of light. The concept of a horizon is fundamental to understanding our place in the cosmos. It is a boundary in space-time. This boundary separates what we can, in principle, observe from what we cannot. The universe is incredibly vast. It might even be infinite, but our view of it is finite. This isn't because our telescopes aren't powerful enough. It's due to the very nature of light and the history of the universe itself. The light from objects beyond this horizon simply hasn't had enough time to reach us since the universe began. The significance of the cosmological horizon is profound. It constantly reminds us that our knowledge has limits. It shapes our cosmological models and theories. Understanding this horizon helps us piece together the story of the universe. From the Big Bang to the present day, the horizon has been expanding. As the universe ages, more light from distant regions reaches us. This means our observable universe is growing, but there are complexities, as we will see, due to the universe's expansion. So when we talk about the edge of the universe, we are often referring to this observable boundary. It's a dynamic concept, not a static one. It challenges us to think about what might lie beyond. Are there more galaxies, more stars, perhaps even different laws of physics? The cosmological horizon is our window to the grand cosmic drama, but it's a window with a frame. What we can see is astounding. What we can't see sparks our deepest curiosity and drives further exploration. Scientists talk about a few different kinds of cosmic horizons. Each one tells us something unique about our universe. The first is the particle horizon. This is the most common one people mean by cosmic horizon. It represents the maximum distance from which light could have traveled to us since the beginning of the universe. Think of it as a sphere around us. Anything beyond this sphere is currently invisible because its light hasn't reached Earth yet. The particle horizon is constantly expanding as time goes on and more ancient light arrives. Then there is the cosmic event horizon. This horizon is a bit different. It marks a boundary in space-time beyond which events will never be observable by us. This is due to the accelerating expansion of the universe. Galaxies beyond this event horizon are receding from us faster than light, not because they are breaking the cosmic speed limit locally, but because the space between us and them is expanding so rapidly. Light from these galaxies emitted now will never reach us. It's like trying to swim upstream against an ever-quickening current. Another important concept is the Hubble sphere. This is a spherical boundary around an observer. At this boundary, objects are receding from the observer at the speed of light. This recession is due to the expansion of the universe, described by Hubble's law. Objects inside the Hubble sphere recede slower than light. Objects outside recede faster than light. It's important to note that we can still see light from objects currently beyond our Hubble sphere. This is if that light was emitted when the object was closer and inside the Hubble sphere. These horizons are not physical objects you could crash into. They are conceptual boundaries defined by the interplay of light speed, cosmic age, and cosmic expansion. The particle horizon tells us about our past observable universe. The event horizon tells us about our future observable universe. The Hubble sphere relates to current recession velocities. Understanding these different horizons helps us map out our cosmic neighborhood. It also helps us understand what parts of the vast universe will forever remain a mystery to us. One of the main reasons we can't see beyond the cosmological horizon is the finite speed of light. Light travels incredibly fast, about 300,000 kilometers per second. But it's not infinitely fast. When we look at distant objects, we are seeing them as they were in the past. This is because it took time for their light to travel across space to reach our telescopes. If an object is too far away, its light simply hasn't had enough time to complete the journey to us since the universe began. This creates a natural limit to our vision. The age of the universe is another crucial factor. Our universe is about 13.8 billion years old. This means that light has only had 13.8 billion years to travel. So we can only see objects whose light has taken 13.8 billion years or less to reach us. This defines the radius of our observable universe. Objects might exist beyond this distance, but their light started its journey too late or from too far to be seen by us today. The universe had a beginning, the Big Bang, and that sets a starting gun for light's cosmic race. Compounding these limits is the expansion of the universe. Space itself is stretching. It's like baking raisin bread. As the dough or space expands, the raisins or galaxies move further apart from each other. This expansion causes the light from distant galaxies to be stretched. This stretching is called redshift. The further away a galaxy is, the faster it appears to be receding from us, and the more its light is redshifted. For very distant objects, this expansion can carry them away from us faster than their light can travel towards us. So it's a combination of these three things: the finite speed of light, the finite age of the universe, and the ongoing expansion of space. Together, they create the cosmological horizon. It's a fundamental feature of our universe. We are limited to observing a patch of the cosmos, albeit a very large one. This doesn't mean the universe ends at this horizon. It simply means our ability to directly observe what lies beyond is cut off by these cosmic realities. It's a horizon of knowledge, always beckoning. General relativity, Albert Einstein's theory of gravity, plays a key role here. It describes gravity not as a force, but as a curvature of spacetime caused by mass and energy. This framework allows for the expansion of the universe. The equations of general relativity predict how spacetime can stretch and evolve. This stretching is what creates phenomena like the event horizon. Certain solutions to Einstein's equations naturally lead to horizons, boundaries beyond which information cannot pass. It's built into the fabric of spacetime itself. Then there's cosmic inflation. This is a theory about a period of incredibly rapid expansion in the very early universe, just a tiny fraction of a second after the Big Bang. Inflation proposes that the universe expanded exponentially, much faster than the speed of light. This sudden, immense stretching could have pushed vast regions of the early universe far beyond what would later become our particle horizon. So the universe we see might be just a small part of a much, much larger cosmic structure, made unobservable by this early inflationary burst. What this means is that there could be an enormous expanse of universe beyond what we can currently see. These regions are not just slightly out of view, they might be causally disconnected from us. The light from them hasn't reached us, and due to ongoing expansion, it might never reach us. The universe beyond our horizon could be similar to ours. Or it could be wildly different, with different physical conditions or even different physical laws. We simply don't know for sure, and that's a tantalizing thought. The existence of these horizons has profound implications. It tells us that our understanding of the universe will always have an observational limit. Future astronomical research will continue to push against this boundary. We can study the cosmic microwave background, the oldest light we can see. We can search for indirect clues about the universe beyond. But the horizon remains. It encourages humility, it fuels our imagination, and it reminds us that the cosmos is full of mysteries waiting to be pondered even if they can't all be directly seen.